Hello, good afternoon. This is Darryl Peterson with Micromeasurements. I'm the manager of the Applications Engineering Department, and along with me is one of our senior applications engineers, Paul Millard. And this afternoon, we're going to take you through a presentation titled Strain Gauge Sensors in a Nutshell. We're basically going to try to give you a sneak peek a little more in depth into strain gauges and maybe a little bit more about a little bit of the history and also some of the advancements that we've been working on. We'll talk a little bit about the advanced sensors and how that is changing the landscape of strain gauges. So I'd like to go ahead and get started. The strain gauges basically can help bridge the gap between the calculation of stress and the measurement of strain. As we all know, stress has to be calculated, whether you calculate it from the response of a strain gauge or you calculate it based off the theoretical assumptions or maybe a finite element model, you still have to calculate it. And the strain gauge is that tool in your tool belt or in your vest that you can use in order to measure the strain, and using Young's modulus and some other material properties, you can end up calculating stresses.
What is a strain gauge, though? A strain gauge is a sensing device which, when it's attached to the length of the surface, its resistance will change as the surface is deformed. So the micromeasurements foil strain gauges are inherently precise measurement devices that are capable of resolving very, very small amounts of deformation, typically expressed in the order of parts per million, or microstrain. A strain gauge is a component used in an electrical circuit. In other words, you wind up with an electrical representation now for that deformation, and the components in the electrical circuit will exhibit some opposition to the flow of electrical current or resistance that can be then correlated to an output to an instrument. So the strain gauge, when it winds up getting stretched or compressed in response to the structure's movement, in response to an applied force, you now have an electrical resistance change that will represent that movement that is directly proportional via the strain. By measuring the electrical resistance change, you then have an exact known correlation to the structure's movement.
So what is mechanical strain? When a body is stressed, the body is deformed, and the strain is a measurement of the deformation or change in shape of an engineering body. A good example is a rubber band. When a rubber band is stressed, it becomes longer and thinner, and that change in length compared to its original length is strain. And there's really one of the major advancements we've had recently in strain gauge technology is the introduction of our advanced sensors line of products. And this is a new technology we use during the manufacturing process that allows us to manufacture strain gauges that are smaller and much higher resistances than ever before. And these strain gauges can be used for two different paths or two different applications.
The two distinct groups in which strain gauges get divided into is for folks that are doing stress analysis, that is, using the strain gauge's signal to correlate directly to the stress in the component. Structures can and do break, and that's important sometimes, or sometimes can be dramatic. It's critical to determine whether the object is of the particular material can carry a particular load. If significant true stress is ignored, the cost of not acting is higher, can be higher than the cost of dealing with the problem. In other words, if you're trying to characterize exactly what's going to happen to the structure, whether it's fatigue, whether it's excessive loading, stress analysis is the approach. The other category, the other path the sensor strain gauge can take is with transducers, and that's typically when you're using the strain gauge signal, not necessarily relating it to stress, but relating it to some other mechanical input. So here you have a specific class of transducers, which are devices to translate that mechanical energy into an electrical signal for representation and measuring or controlling something else. That's when you start talking about load cells and pressure transducers, extensometers, things along those lines. Some common examples of the transducers would be to measure fluid pressure, weight, acceleration, displacement, torque, virtually any engineering component that is going to have a linear relationship to what the strain gauge is measuring.
Some common characteristics of strain gauge technology really is that it's a mature technology. Strain gauges were invented back in the 1930s. We've been in business since 1962, and when you think about the electrical resistance strain gauge, some common characteristics come to mind. First off is they can be very accurate. They're widely used throughout the world for experimental testing and widely trusted. They're reliable, assuming you follow the right techniques for gauge installation. It can lead to very reliable measurements. They're also relatively easy to use. Many of the gauges we produce today, such as the C4A series, have pre-attached lead wires on them, so that can really streamline the process of gauge installation. And also, they're relatively low cost. Some strain gauges, you're talking about just a few dollars a piece, and you can get a tremendous amount of information out of spending just a few dollars. And then finally, also, they're quite compact. The strain gauge is an averaging device, but we have strain gauges that go all the way down to 8 thousandths of an inch active length, all the way up to about 4 inches long. But we've got, and really today we can push the limits with the advanced sensors technology and probably even go smaller than 8 thousandths of an inch if the application calls for it. Now there's 4 primary steps involved in setting up a strain gauge measurement. The first real step in that is the selection of the strain gauge. Next would be the adhesive selection. After that would be the surface preparation, making sure that surface is cleaned and ready to accept whatever qualified strain gauge adhesive system that you're going to use. And then really the 4th primary step is the instrumentation, the electronics that you're going to use, sort of like Paul talked about, to convert that resistance change to an electrical response, so then you can amplify it and maybe digitize it and capture and record it.
And really all 4 of those have an equal responsibility in order to make the strain gauge function properly. If you don't address the adhesive or the surface prep or the right instrumentation, the strain gauge becomes meaningless too.
That's right. I would agree. Brief history of strain gauges, I guess, as it relates to the age, and some of us in this room are at different ages than others. But the going back and kind of tying strain gauge development to the age of us, the silent generation was from 1920 to 1945, and that's the era of the carbon powder strain gauge. And then later, baby boomers are 1945 to 1960. This is when these folks returned back from World War II and decided to start having babies. And that really ties to the development of the resistor wire strain gauge. And then the next generation after that, which is my generation, is Generation X, where wire on paper strain gauges were developed. And really, the foil technology was coming along about that era as well. And then you get into some of these newer generations, like my children, and that's the millennials and a Generation Z. And really, you're full into foil strain gauges, and they're widely used in a wide variety of different products. And then you look at today, Generation A, I guess is what it's being called, from 2005 to 2015. And really, the most recent major advancement is the introduction of using the advanced sensors technology for manufacturing the strain gauges, and not only manufacturing it for transducer production, but also manufacturing it for stress analysis applications as well. This advanced sensors technology is used in a wide variety of different applications, some consumer-based products. Many of the load cells and pressure transducers, like Paul had talked about a little bit earlier, and now more recently, the technology is working its way into experimental testing and stress analysis, where, again, we can make the gauges smaller, more compact if needed, We've got a 3-element rosette. There's actually a picture of it here that's intended for printed circuit board testing, that has an active gauge length less than 20 thousandths of an inch. So it has a very, very small footprint, which helps when you're putting strain gauges on electrical circuits and boards. And when you got a limited amount of space, this gauge has a very small footprint to allow you to get it close to these electronic components. And this advanced sensors technology has further improvements over traditional gauge types, including the smaller and tighter grid resistance tolerances, also improved gauge-to-gauge repeatability due to the processing, which leads to really enhanced measurement stability. And all these enhancements are implemented via a fully optimized fabrication process, incorporating some of the latest production processes and tooling methods and the equipment that's being used. And due to this, the prototype design and manufacturing of a strain gauge for anywhere from just a few pieces up to OEM volumes can easily be accommodated, and it produces a very uniform gauge of very high quality, but also a competitive lead time as well.
Okay, well, when it comes to strain gauge selection, there's an awfully wide variety to choose from, which sometimes confuses folks. You start breaking it down in order, somewhat order of priority, but each one of them needs to be addressed in order to choose the appropriate gauge for your application. As we've been describing, the two paths that are often taken right from the beginning is, are you measuring stress, or are you using the strain gauge's signal to correlate it to some other engineering units, something else mechanical other than strain? So that stress analysis versus transducer becomes one of your early decisions. The pattern, there's a wide variety of patterns that are available. We tend to sort our gauges based on the first selection, the first judgment that's made, which is armed with the knowledge that the gauge length is going to average the strain into the grid. You often will choose your pattern based on the length of the grid you need to have. And then, of course, since it's averaging the width as well as the length, the size of the gauge winds up determining the grid size that you're going to wind up working with. Resistance of the strain gauge, well, it's sometimes limited by the instrumentation that you're going to be connecting it to, but in general, if you lean towards higher resistance gauges, it's going to give you more options and more capability in terms of selecting a higher voltage and getting a higher signal from the strain gauge. Of course, as the strain gauges get smaller, you would think that you'd have less and less choices for higher resistance gauges, but with some of the newer production technologies that Darryl had just mentioned, we're capable of generating extremely high resistances in extremely small footprints. Kind of scary, actually, compared to just a couple decades ago, what current manufacturing is capable of doing. Then there's, of course, the question regarding thermal response. As the temperature changes and as your material expands or contracts, you're going to have some apparent strains due to temperature changes, and having the strain gauge temperature compensated to help offset that effect winds up becoming important as well. That becomes part of the process with your strain gauge selection.
And when you look at the different patterns that are available, as Paul mentioned, there's a wide variety of them, from linear gauges to shear to 4-element, 5-tab, full bridge circuits for measuring torque or shear strain. And I would encourage you to look in our catalog or look on our website. You'll see a listing of all these different types of strain gauges, and sometimes it can be a little bit intimidating in trying to select the appropriate one. But that's where, if you do have questions about it, you can reach out to Micromeasurements. We have a full staff of applications engineers that would be glad to help guide you and help narrow your choices down to the appropriate gauge that fits the application. And really, as we look at the DNA of a strain gauge, really this is an image we have in a presentation that shows the alignment marks and the dimensions associated with the gauge, and you'll find these to be in the catalog and on the website. And one of the most important things to recognize is what is the gauge length and the grid width, because the strain gauge is truly an averaging device. So the longer that gauge length, the longer it's going to average. The shorter it is, the less it's going to average. And the more of a strain gradient you have in general, you lean towards smaller size gauges. But you'll see the gauge length and the overall width, as well as the matrix sizes. That's the entire footprint of the strain gauge. And in some cases, you'll find the grid is the right size, but the matrix is too big. And you can trim that using a straight edge razor blade and use it like a guillotine. We typically take the gauge out of the folder, lay it onto a piece of clean glass, and just chop off the extra backing. And the key is to make sure you stay outside of the alignment marks. The gauge, like in this image, you'll see very well defined triangular alignment marks and rectangular alignment marks to help you position the gauge correctly on your part. And as you're trimming it, just try to stay outside of those.
Okay, well, the next slide describes how it takes one steering gauge to build a bridge, and that intra-bridge connections are integrated directly to the pattern itself, and eliminating the need for traditional intra-bridge soldering. The addition of gold-plated solder pads improves solder joint reliability while reducing the risk of solder oxidation prior to lead wire attachment. What that typically means is that some strain gauge alloys are difficult to solder to. We make accommodations wherever possible so that you can easily and more successfully solder to the strain gauge itself.
Now, we've also recently added checklists. These checklists are available on the website. We realize that we have a lot of customers that this may be their first application for strain gauges, and we've tried to come up with the ability to make this gauge selection, adhesive selection, instrumentation selection easier. And we've kind of grouped these into different products. So we've got a checklist, for example, for composites such as maybe plastics or fiberglass. We've got one for aluminum. We've got one for glass, like if you're testing the windshield of an aircraft. We've got one for concrete. Typically, you're using epoxy-based adhesives and bigger gauges. We've got a checklist for steel, which is a very common material that gauges get installed on. And we also have a checklist if you're that manufacturer of electronic components and you've got an application to put gauges on a printed circuit board. We've got that checklist as well. And the next slide kind of shows you an example of what these checklists look like. We focus not only on the strain gauge, but also the adhesive selection and also the instrumentation selection, trying to sort of guide you through your application and help you with the right type of selection. This one happens to be for composites and plastics. And of course, you have a wide variety of choices, and you may find that you choose a product that's not listed on this checklist, and that's okay. But this is really intended to help give you a guide and kind of point you in the right direction. And we like to think of ourselves as one-stop shopping. When you come to Micromeasurements, we're going to help you from A to Z. We can help you with the strain gauge selection, the adhesive selection, how to clean the surface, how to prep it, get it ready for bonding, and we also offer instrumentation. So we can help you not only with the gauge installation side, but also with the instrumentation so that you can take very accurate strain gauge measurements.
In terms of, we talked about the 4 areas that are to be factored in. One of them included surface preparation. Micromeasurements offers a variety of accessories that, again, once you go through a checklist and find out what perhaps you can and cannot do with the material that you're working with, we offer the accessories to address the fundamentals. And some of those fundamentals are summarized here, where we talk about solvent degreasing. Sometimes you may be able to use aggressive degreasers, an aggressive solvent degreasers. Other times you may not be allowed to and have something more passive. Again, we have a variety to help support that. Commonly used a second technique, or second step would be abrading, which is to remove any sort of contaminants, whether it's plating, whether it's paint, whether it's oxidization of the material. It often involves a dry and a wet abrading of the surface to mechanically prepare it. And then applying layout lines. In other words, coming up with a strategy to help find the location of where your gauge is going to be positioned And conditioning and neutralizing, those are two chemical steps. Conditioning is often combined with a wet abrading process, in which you are chemically etching the surface to remove contaminants and oxidization, and then neutralizing to get the surface to a proper pH level in which a strain gauge adhesive will want to adhere to.
When it comes to adhesive selection, strain gauge performs really no better than adhesive that's being used to bond it to the test surface. And this is obviously a key component of a successful strain gauge installation, is making sure you select the right type of adhesive system. We get this question a lot, what's the difference between a strain gauge qualified adhesive and one that's not? And the way I look at it is you can take about anything and glue a strain gauge down onto a surface. The question is whether or not it's going to be able to transfer strain. And well-bonded strain gauges typically exhibit three characteristics. They've got good zero return. When you load it and release the load, they go back to where they start. They have excellent stability under a constant load. And then third, they're also very repeatable. So when we look at different adhesive systems and we're qualifying them for strain gauge use, those are the types of criteria that we're looking for: zero return, stability under load, and repeatability. And since there's so many different applications, there's really no single adhesive that's well suited for all of them. So we have a selection of over a dozen different types of qualified adhesives for strain gauge measurements. Everything from stress analysis to building a very high precision transducer. And every one of our adhesive systems that's offered by us has been formulated in-house, and it's sourced from a qualified third party, and it gets extensively tested in our micromeasurements engineering department to make sure it's up to the task. And once you get the gauge installed, one of the other areas you have to think about is how to protect it from the environmental conditions to which it will be subjected to. And strain gauges can easily be degraded by the presence of moisture or chemicals or sometimes mechanical damage, things like rocks and gravel bouncing up and hitting it. So not only do we offer a wide range of adhesives, but we also offer a wide range of environmental coatings. And you have to select them based off of the conditions of your environment, as well as maybe the longevity of how long the gauge installation has to last. So we offer protective coatings ranging from simple brush-on coatings like our M-Coat A, which is a polyurethane protective coating, to something much more protective in terms of mechanical and also moisture protection like our M-Coat JA. It's a 2-part polysulfide. You spread it on about like peanut butter, but it offers up excellent chemical resistance, mechanical protection, and moisture protection as well. And while it's often practical in lab applications, sometimes you can use strain gauges without adding the additional protection, but 99% of the time we want you to be using an environmental protection over top of the strain gauge. That helps to protect the sensor. In many cases it also helps to hold down the lead wires. It keeps ambient humidity off of the gauge installation and off of the adhesive system. In particular, if you're using a cyanoacrylate-based adhesive, you really ought to be using a protective coating over the top of it.
We also offer a range of instrumentation that's anything from a single channel device that's quick and easy to use, simplified, to portable indicators that are more easy to take out into the field, to multi-channel data acquisition systems with high bandwidth signal conditioners, standalone signal conditioners that would act as a front end for other devices. So since we specialize with strain gauge measurement, we wind up paying attention to the needs of what the unusual and demanding needs are for strain gauge signal conditioning. It typically will also avail itself to other types of sensors, typically strain gauge based load cells, displacement transducers, but also thermocouples and accelerometers. Our special purpose equipment complements the strain gauges, installation integrity, and instrument calibration. We also have a simple single-channel device. It's summarized here as the student DAC, in which you can monitor strain, force, temperature used with a student DAC. It's a single-channel USB device, inexpensive. You'll be able to hook it up to a laptop or a desktop and be able to monitor strain gauges and transducers. It does provide bridge completion, and it can be used with more than one strain gauge if you have more than one student DAC. Software is supplied to be able to control and manipulate the information, the signal coming from this device. The P3 strain indicator and recorder is a very popular 4-channel device, portable, battery powered, stands alone, but it does have a USB connection in which it brings up a very nice display on a laptop to be able to operate and utilize the P3. It does provide critical bridge completion, shunt calibration, and the software involved with that. It also will record data onto an SD card for being able to retrieve it later on. It actively will display all 4 channels on the display and independently be able to articulate any of the 4 channels, whether you want to zero, calibrate, and adjust. In addition to making strain measurements, it'll also work with other strain gauge-based transducers. So with a simple entry of millivolt per volt sensitivities for whatever full-scale value, it'll act as an indicator for a strain gauge-based load cell.
Typically where we find strain gauges, it can really cover a wide variety of different types of testing conditions and different types of products. I kind of mentioned this before, but strain gauges, you can certainly find them in experimental testing, whether it's construction equipment, automotive testing, maybe more of a civil engineering based type project where you've got bridges or large steel structures and you're trying to measure the load. A more recent application that's gotten pretty popular over the last probably 10 to 15 years is printed circuit board testing, where manufacturers of equipment that we use every day in our homes and sometimes on our way to work, they are trying to qualify this equipment so to make sure that it survives not only when you're using it, but more important in many cases to them, it survives the production process in their own facility. Oftentimes, a very high percentage of the loading conditions that these boards are subjected to happen during the manufacturing of the boards. Things like in-circuit testers and depaneling of the boards where they take a big board and they cut it into smaller pieces. All that can put, in some cases, excessive strains on the electronic components, and the gauges can be used to qualify that and see if they need to streamline their process. So there's a wide variety. You name it, there's a good chance that a strain gauge has been put on it at one time or another. This next slide shows that strain gauges sometimes can be used for the more not typical applications, such as biomedical type studies. Years ago, they were working on artificial heart valves, and strain gauges were an integral part of trying to determine the lifespan of these artificial heart valves. Also, dental studies have been done as well, where when they're looking at new composite materials to fill a cavity, oftentimes when they're filling cavities, it's a multi-step process where they put a little bit of material in and they cure it, and put a little more in and they cure it, put a little more in and they cure it. And more recently, we worked with the local university where they were trying to do a one-step process, and they were looking at how that changes the tooth, and the way that changes the tooth, they measured it using a strain gauge. Companies that manufacture equipment such as satellites, they certainly use strain gauges in their qualification. And if you're looking for maybe testing some plastic, some 3D printed plastic materials that maybe you're using for modeling, you could consider using strain gauges for that as well. We also find them being used in more of a consumer-based product. I'm sure all of us have seen these bicyclists like Lance Armstrong, and during the training, if you ever wondered how they measure how much power that these bicyclists would put out, One of the ways to do that is to instrument different components of the bike, whether it's the rear hub or maybe the pedals or the crank. And all three of those get instrumented with strain gauges so that they can monitor the amount of torque and therefore calculate power that's being generated by the athlete that's on the bike. You might also find strain gauges used in equipment like combines where they're either doing structural testing of the combine, or in some cases they might be measuring the amount of material that it's harvesting. And in farming, they also measure how much material they're putting out on the field whenever they're fertilizing it. And there's some companies set up to specifically make products just for that industry. It basically makes the farmer smarter about where he's putting his fertilizer and how often he needs to do it. And then, of course, the Internet of Things, strain gauges, we see them used a little bit more today in products that are more consumer-based. Things like if you're ever wondering where you see a device that takes a load or force input and converts it to an electrical response, there's a really good chance that a strain gauge is at the heart of it. Whether you're in the supermarket or you're driving down the highway, or maybe you've purchased a component that you're going to use with your computer, if it's sensitive to force, there's a real good chance that a strain gauge is at the heart of it.
Of course, some of the best ways of learning is by example of what others have done and perhaps have failed at doing. And so there's a lot of information that's out there and available to you. Strain Blog is an excellent summary of different approaches, different techniques. You may feel that you're on an island doing the only person considering a certain type of measurement, only to find out that it's been done before and it's been shared, and you can find it.
So minimizing strain gauge-induced temperature measurement errors when using bondable RTDs, along with strain gauges, which is what we've spent the majority of our time discussing, we also manufacture a line of RTDs. They're resistance temperature detectors, and they look just like a strain gauge, but they're made out of basically a pure nickel foil, and that nickel generates a resistance change as a function of the temperature changing. And we can offer these in an application where not only you're sensing strain, but you need to sense temperature. And along with these RTDs, we add a device that's called an LST matching network that helps to linearize the resistance change so that you can connect it directly into a strain indicator like Paul had talked about earlier, like the P3 or even the student DAC. You could connect the LST network directly to the student DAC, and instead of monitoring strain, you're monitoring temperature.
And one would normally select an RTD over a thermocouple when you're looking at more rapid response to a temperature change perhaps, but also greater resolution. So we're talking down to tenths of a degree rather than 1 degree resolution typically with these sensors.
So just to kind of summarize, strain gauges in general, we consider them easy to use. We do offer workshops that we teach on a monthly basis to help you get over that initial learning curve. They've been very popular. We've done them for many, many years, and they're usually very well received to teach you how to properly use the strain gauges. And it's sort of like learning the right recipe. We could all be good cooks if we can follow the recipe, and that's really what we're trying to teach you is the recipe behind a successful strain gauge installation. And when you consider their accuracy, typically the experimental stress analysis measurement under ideal conditions, typically you can push upwards around 1% type accuracies, probably even better, depending on how you can control the variables in your test. Micromeasurements is a one-stop shop. We like to think that we cover everything from A to Z, from the strain gauge to the installation accessories to the instrumentation to the technical support, both before you purchase the product as well as afterwards. We also offer strain talks where we have local technical sales managers that can come in and discuss strain gauges and instrumentation in general, and then if they need more support The applications engineers will often be traveling with the technical sales managers, and they can come in and get a little more in-depth related to very specific topics that would be defined before we traveled. Local technical support, that's really through the technical sales manager and our staff here at Micromeasurements. We take that very seriously, and we pride ourselves on providing very good technical support related to strain gauges. And like I mentioned, we have workshops. We have a 2-day class that we teach on the road, and then a 3 and a 5-day class that we teach here just outside of Raleigh, North Carolina. And on average, we teach more than 1 workshop a month. So if you're interested, there's a real good chance that you can find a workshop that'll help to meet your needs within the timing that you need as well. And consider Micromeasurements, like I mentioned, a comprehensive solution. The strain gauges, the accessories, the instrumentation, the training programs, everything pretty much from A to Z that you'd need related to strain gauges. Reached the end of our presentation. I want to thank you for taking the time to spend a few minutes with us and take a look at strain gauges in a nutshell. If you have any questions related to strain gauges, please feel free to reach out to us. You could call us at 919-365-3800 and press 2 for applications engineering. You can also find a wealth of information on our website at www.micro-measurements.com. We thank you for taking the time, and on behalf of myself and Paul Millard, we thank you and have a great day.